Hello, in this video we're going to look at the Nobel Prize in Physics 1917, awarded to Charles Glover Banks for his discovery of the characteristic Roentgen radiation of the elements, another important step in the development of X-ray spectroscopy. Here you see his diploma. There's some information on what he did. Following the discovery of X-rays, it was soon established that an irradiated compound emitted secondary X-rays. In secondary X-ray spectra, lines appeared corresponding to different wavelengths. Around 1906, Charles Barkla proved that each element's secondary spectrum was unique, irrespective of temperature, structure, and chemical composition. The spectrum was therefore a characteristic property of an atom, and thus became an important tool in atomic research. There's some biographical information coming from, of course, as always, the official Nobel Prize site. Charles Glover was born on June 7, 1877 at Widnes, Lancashire, England, where his father was a secretary to the Atlas Chemical Company. He was educated at Liverpool Institute and entered University College Liverpool in 1894 to study mathematics and physics, the latter under Oliver Lodge. He graduated with first-class honours in physics in 1898. In the following year, he obtained his master's degree. Also in 1899, he was awarded research scholarships by the Royal Commissioners for an exhibition of 1859. He proceeded to Trinity College, Cambridge, to work in the Cavendish Laboratory with H. Thomson. He migrated to King's College during 1900, and in 1992 he returned to Liverpool as Oliver Lodge Fellow. From 1905 to 1909, he was awarded successively demonstrator, assistant lecturer in physics, and special lecturer in advanced electricity at the university, and in 1901 he succeeded E. H. Wilson as a Western professor of physics in the University of London. In 1903, Barkla accepted a chair in natural velocity in the University of Edinburgh and held this position until his death. Barkla's first researches concerned the velocity of electric waves along wires, but in 1902 he commenced his investigation on Roentgen radiation, which was probably all of his whole life. His discovery of homogeneous radiation characteristics of the elements showed that these elements had their characteristic line spectra in X-ray, and he was the first to show that secondary emission is of these two kinds, one considering the X-ray rays scattered unchanged and the other of a fluorescent radiation peculiar to the particular disciplines. He discovered the polarization of X-rays, an experimental result of inconsiderable importance, for it meant that X-ray radiation could be regarded as similar to ordinary light. Barkla made a valuable contribution to present knowledge on the absorption on the photographic action of X-rays, and his later work he demonstrated the relation between the classic X-ray radiation and the corpuscular radiation accompanying it. He also known both the applicable and limitations of the quantum theory in relation to Roentgen radiation. Results of his findings are recorded in various papers, which have appeared mainly in the translations and proceedings of the Royal Society, and he had a considerable reputation as an examiner in physics. As you can see, this is also coming from the official Nobel Prize site. You can follow the link. Here you can see some illustration of the electron transition between shells, and each shell has a certain energy, and if an electron shifts from one shell to another, you have to put in or put out some electric energy, of course. Then there was one speech given by Professor G. Grandquist, summarized by me. When X-rays fall on a substance, they cause a secondary radiation that was discovered by Sanyek in 1879. Professor Barkla of Edinburgh has discovered a new and unanticipated phenomenon which has turned out to possess the utmost importance for physical investigation. The secondary radiation consists of two varieties of radiation wholly differently from each other. One is a corpuscular radiation of the same characteristics as cathode rays, and as the analogous rays of radioactive substances being an emission of electrons. The other, on the contrary, is of the same characteristics as X-rays. Barkla has made a long series of very careful investigations into the nature of the latter of the two types of radiation. In the first phase, he discovered that there are two different kinds of X-rays, and in the secondary radiation, the absorption coefficients of one of these two varieties are the same as those of incident X-rays. Thus, the X-rays have some penetrability as the primary rays, and as they prove in other spectra have the same qualities as primary rays, they must be regarded as a diffuse primary radiation. The intensity of this diffuse radiation varies in different degrees in relation to that of the incident primary radiation. By measuring the distribution of the intensity of the diffuse radiation, Barkla was able to determine the total emission of a series of substances under varying conditions. One very important result among others that this investigation led to enabled Barkla at an early stage to estimate approximately the number of electrons contained in an atom. The other variety of X-rays is wholly independent of the characteristics of the incident radiation. Barkla showed that this radiation is homogeneous, that its absorption coefficient is not dependent on the incident radiation, but is determined by the irradiated substance. Further, he made the important discovery that the character of the rays is solely dependent on the qualities of the atoms constituting the substance, independently of the chemical composition of the substance. Every chemical element yields a secondary radiation that is characteristic of that element. This variety of radiation may be most conveniently studied in the element of relatively high atom weight, for in them it is stronger than the diffuse radiation. The characteristic radiation, however, being in contrast to the diffuse radiation perfectly homogeneous, can be distinguished from the latter, and this Barkla could trace the characteristic radiation down to the element of the atomic weight of 27. The characteristic radiation is furthermore, in contrast to the diffuse radiation, wholly impolarized and is not dissymmetrical in respect to the direction of incidence of the primary radiation, but expressed uniformly in all directions. As the characteristic radiation originates from the X-rays, the emission of this radiation must be accompanied by an absorption of X-rays. All such factors as density, temperature, state of aggregation, and chemical composition prove to be without essential importance. The qualities of the atoms alone therefore determine the account of the radiation. The absorption is furthermore selective, and as with regard to light, those rays are preference absorbed that the substance emits as those temperature, so it is here. The atoms absorbing preference those rays that the atoms are emitting in the forms of characteristic radiation. Another striking resemblance between light and the X-rays has been discovered by Barkla, just as in agreement with Stokes' law, fluorescence can only be generated by light of high frequency, so too the characteristic radiation requires for its radiation a greater penetrability of the primary rays. Barkla's discovery that two domains of differing hardness are to be differentiated in the characteristic radiation is fundamentally important as regards to the modern conception of the structural atom. Barkla has named the two domains the K series and the L series respectively. Thus, every chemical element, when irradiated by X-rays, emits two rays of different permeability. That's to say, every element can, for instance, emit an X-ray spectrum of those two lines or line groups, the so-called K-series or X-series. Of these, the K-series have a greater permeability. Barkla succeeded in following the K-series from calcium to cerium, the L series from silver to bismuth. If these rays are defined, for instance, the terms of their absorption in aluminium, the set absorption for rays belonging to the one and same series to be approximately a linear function of the atomic weight of the element that emits the radiation. By arriving at that conclusion, Barkla had on one hand furnished the most indisputable proof that every chemical element possesses a characteristic X-ray spectrum of its own, but on the other hand it has made manifest by this investigation that the set characteristics spectra, in contrast to all other spectra for known, do not display any periodic qualities in connection with the place of the elements in the periodic system. The discovery of the diffraction of X-rays in crystals gives a means of measuring their wavelengths, and since then, the further investigation of the K-series and L-series has yielded results of fundamental importance as regards to our perception of the inner structure. Suffice it to say that those investigations have shown that it is the electrical charge of the nucleus of the atom that determines its place in the periodic system, not as it has been if you assumed its atomic weight. The former is in its general half to the latter, but its differences of the rule are due to irregularities in the distribution of atomic weight amongst elements. The charge of the nucleus being the factor that determines the chemical attributes of the atom, it has also been possible to establish the fact that of the chemical elements there are now not more than 6 that are known. Black's discovery to collect the X-radiation of the elements reveals the phenomenon of the intermittent portion of the study of the inner structure of the atoms. As you can see, this is coming from the official Nobel Prize site. Next week, we will go into the Nobel Prize lecture given by Mr. Barkla. For now, thank you for watching.